Okay, well, I just wanted to point out we had 2 colloquia canceled due to the government shutdown. The first due to being a government employee, and the second one due to the travel mess up due to the government shutdown. But in this case, we had an emergency backup colloquium speaker flew all the way from China. Moments notice. And so Norbert is going to introduce today's speaker.
All right, welcome everyone. Glad you can make it to the colloquium. So we are very fortunate that Kihwan Kim is visiting us from Tsinghua University in China. Use the microphone. Oh, I can use the microphone too. Good. Hello.
Test, yes, there you go. We are very fortunate to have Kihwan Kim visiting us. He did his undergrad and his PhD at Seoul National University in South Korea, and then he did a postdoc with Rainer Blatt in Innsbruck, and then he did another postdoc with Chris Monroe here in Maryland, and then he became a professor at Tsinghua University. He works in trapped ions and quantum simulation with trapped ions and also quantum computing, and he's going to talk about the longest coherence time ever measured in any qubit. And so looking forward to your talk, Kihwan, and welcome.
Thank you for your kind introductions, and also I'm really honored that I can give a talk in this colloquium due to maybe Norbert and Elena the finding a way to now talk about our research. And I did the postdocs from 2008 to 11 with Chris Monroe, and I remember really I had attended several colloquiums. One of them was Alana Space and so on. So I cannot believe I can give a colloquium at this place. So really thanks a lot for giving me this chance. And today I'm going to talk about so very long coherence time, about 10 hours. And what's the deal about it? I'm not sure if this is really important work or not. But anyway, that's pretty simple to understand. I believe I need most of people see what's going on in this field, and also maybe if I believe there is more time, then we are talking about some other scaling experiment and so on. So let me first introduce myself. Already Norbert introduced me very clearly. So I did everything in South Korea, and then after PhD, I had another postdocs, and then first did with Rainer Blatt in Innsbruck, Austria, and then I realized still I'm not good enough to do something by myself. And then at the time, Chris Monroe moved to from Michigan to Maryland. He expanded his setups and so on. So I had a chance also working with him. So from 2008 to 11, in this the University of Maryland, I must say one of my best times in research careers here. So again, anyway, then I had a chance to go to Tsinghua University in China, though I never imagined that place. But anyway, I also had a great experience in China, and then now in end of this year, I'm starting new positions in South Korea. And anyway, this is my brief introduction. And so let me just briefly go through. So we all maybe hear about this quantum field and so on. So eventually, this control number of qubits is increasing. Then the classical computer eventually is more or less saturated or linearly increasing capability, but maybe with quantum, the Hilbert space goes exponentially. So whatever exponential speed up in computation or information processing can happen. We imagine about it, and then people still trying to find some application, not fully clear where to apply and so on. Maybe some security or optimization or molecule or just some material design understanding, something like this. We are still exploring about it. But nowadays, including companies and many also the startups involving. So somehow there are many here and there noises and also because of that, pushing this technology, a lot more happening. And as this technology going on, so simply we can summarize how much is developing is the number of qubits is getting more increasing. Also, all the controls are getting better and so on. So nowadays, we are around hundreds levels of qubits we can manipulate with a pretty decent error levels and so on. And then I can see this kind of development just going faster and faster. So we don't know where and how we can end up millions of qubits and much better gate fidelities and so on. And this field is rapidly moving on. And then in these times here, what we are trying to address is what is basically ultimate qubits. So all this quantum capability comes from we can have some kind of superposition state. So the superposition, basically, we think of a two-level system, whatever frequency is separated, and then this one, we can just put in kind of block sphere, and so that we just mathematically putting down and up in together, this kind of mathematical notations. But anyway, this superposition capability, extend to multiple number of qubits and so on. That's somehow the essence of quantum computations. And so which one, so the basic problem, it may be reduced to the single qubit first. So what is the really best qubit or perfect qubit or ideal qubit we can imagine? So the first criteria we can say is maybe this superposition staying capability. One of them is called T1 time, so the zero decaying. So whatever of state, typically atomic state is going down. Also, whatever superconducting systems and so on. So once we have whatever prepared state, it shouldn't never decay. So that's maybe one criteria we can imagine. And then, as you know, the hyperfine ground state of hydrogen that has roughly estimated about 10 million years. So if our qubit is one of state, basically it will be there forever. And then another criteria should be the dephasing error. So when we have this superposition, there is some kind of phase there. And also this phase evolving with the time that related to frequency difference. And then we know for example, hyperfine ground state of cesium. This is the exact frequency we know. So in that sense, we can think this hyperfine ground state of an atom could be an ultimate choice. So this is pointed by Kihwan Kim, and I think this is one of, for me it's a reasonable argument, but if maybe other community people could have some different ideas. But anyway, we think no matter what eventual winner of quantum system, maybe either quantum memory and so on, maybe these atoms still we may need. So this is one aspect I'm trying to say about it. So any objections? Any different opinions? Okay, then let me move on. Thank you for agreeing with me. In that sense, then which atoms we can use? So this is made by IonQ company, and then for the quantum technology, so basically the trapped ion system or neutral atoms, maybe photons, are using natural qubits. So basically either atomic ions or the really neutral atom, they may have a capability have infinitely long coherence times or superposition capability. But I would say the neutral atom, compared to neutral atom, ion trap is better because it's trapped by trapped by electric field, which is much stronger than laser. So once you hold it, it may there forever. But neutral atom case, maybe second, maybe minute level, you can hold, and then most likely it's gone. But that's very different aspect. So although both are same atoms, one has charge, the other is not. The ions showing much longer coherence time because we can hold really more or less infinite times in principle. So I'm really emphasizing this ion system. So if you look at the past coherence time development, so this is a year, vertical axis is seconds, and then the NIST groups, Dave Wineland groups showed about 10-second level, and Oxford groups shows about a minute level, and then we had we had a chance to 10 minutes or an hour, something like this before, and I'm not really trying. Please not offended by this slide if we are doing anything about superconducting system. So originally I saw in the website this kind of superconducting systems coherence time development, and it's very impressively increasing. Nowadays it's reaching to the millisecond level, and the people believe maybe the millisecond would be the longest times that you may be able to achieve. So this is about millisecond is bound. But then on top of that, I just extended this log scale. And then this is now the seconds and thousands of seconds, something like this. So the really trapped atoms and hyperfine ground state can be really ultimate ideal the qubits. So one of our works we had about 10 minutes, and then later we had about more than hours. Coherence times things and so on, and but today, as you see in the title, we somehow extend to another order about 10 hours. So how that happened is starting with this trapped ion system. So in trapped ion system, basically we have some vacuum inside. There's some kind of trap structure that. Using oscillating electric field and holding atoms, something like this. So once we holding atoms, then it's more or less stay there. You can roughly say it's thinking more or less forever. I'm a little bit exaggerating, but it's stay there really long times. And in this bright spot one by one, all is really single atom. So you can see really single atom, so fluorescence with camera in this trapped ion system. Also same to the neutral atoms. But anyway, it's individual qubit. We are using ytterbium's the 171 ytterbium, hyperfine ground state, which just take the 2 level, and that's our qubit. And here, and then on top of that, I just briefly want to say the lots of ions have this shared collective vibrational mode, and then also this is central mass mode and the breathing mode and the higher order mode and so on. There are many modes is there. So basically these are all about trapped ion system. So individual qubit and then the vibrations that can be considered as each one as one harmonic oscillator with some specific frequencies. And with that, typically we start with Doppler cooling, so laser cooling, and the ground state cooling developed by Dave Wineland. So we just cool down the atom a little bit smaller than millikelvin regime. So our system itself in room temperature, but individual atoms can be cooled down really low temperature, something like this. And then by using called the optical pumping technique, specific lasers related to this energy level. In a very short time, we can initialize everything to the down state. And then if you look at the camera, looks like a gun. Well, it's not, just the state is down. And then we do something in between. And in the end, we just detect this individual atom. And then depending on our state is up state or down state, we can see the atom or nothing like this. So this is how we ended up. Finally, we detect the state. And in between, we do so-called single qubit operation. If you have a laser beam that has a frequency difference exactly matching to the qubit frequency, then we can do the Rabi oscillation. And then for the 2 qubit gate, it's rather complicated. So today I'm not talking about much about it, but basically using all this vibrational mode that we just saw, and have any all-to-all types of everything connecting gate can be realized. So as an example, this is one ytterbium atom, and initialized to the down state after Doppler cooling. And then if we apply the microwave and then detect, our signal looks like this. So now this atomic population is going back and forth. So in the beginning, everything is initialized to the down state, and we need to repeat 100 times or many times. So if we initialize it down, then we cannot see anything. No fluorescence comes. And then after applying microwaves some time, we can see everything now to the upper state that has a fluorescence. So then after repeating 100 times, we do see atoms 100 times. So that's why relative probability is 1. And then in between, half a chance we do see atom, half a chance we don't see. So it's a kind of indication of we are in superposition state. So basically now all about this measuring coherence time is when we're preparing this superposition state, how long does it last? That's all we are asking about it. And it's very simple question. So, and as I briefly mentioned, in the around 2005, Dave Wineland group in this is atomic levels of beryllium ion, beryllium 9 ion, and then depending on magnetic field, energy levels separating and so on, and then particular this energy level at this particular magnetic field is the first order magnetic field insensitive state. So then they show the pretty long coherence time, about 10-second level. So you see they measure up to 6 or 7 second level, and then extrapolating this contrast and 1/e decay times, that's more or less people define as coherence time. And similar things done with Oxford groups. Oxford group case, they use a calcium 43 ion, some different magnetic field strength. So again, that energy level is magnetic field insensitive state, and measuring up to the 15, 16 seconds, and by extrapolating, it shows about minute levels of coherence time. So this superposition exists, they extrapolate to about this minutes. But we already know this hyperfine qubit never decays. And also the dephasing time in principle could be infinite. But what's the problem? Why we are limited by either 10 seconds or minutes? So that's what we are wondering about. When we think about these issues, why we think about this one? Because when I had a chance to meet Charles Bennett, who developed quantum cryptography with photons and so on, and one day I just suggested him, maybe we can use atoms for quantum cryptography instead of photons. And then he was so angry at me, and he said, you atoms property cannot be used for cryptography anything. If we want to show anything more than at least hours coherence time, if we show it, then maybe we can talk about it. So I thought already people realize over our coherence time with atoms. And so I digging out, I realized not yet done. So I met him around 2015. So the Oxford group's minute was record. I didn't know how to fight back to him. So I checking out what's the problems. Why is it limited to about minute levels? Maybe nobody knows much better. But later we realized that the problem is not about atom. It's basically problem of laser cooling. So when we first do the laser cooling with a laser beam, and in order to maintain this coherence, we have to turn up the light. Then because of nearby noise and so on, so this ions heating up. It's heating up quite some speed. So after 10 seconds or 20 seconds later, now it's moving pretty fast. So the heating of the ion without the cooling laser beam makes the ion is moving pretty fast. So Doppler shift contaminate the fluorescence detection that we just discussed. So it's not atoms losing coherence, but we cannot just simply detect. We shouldn't see any fluorescence, but because of ions moving, we do see the fluorescence, and we should see the fluorescence, but because of ions moving, sometimes we didn't see it. So this one clearly pointed in this Roy's paper when they measure about more than 10 seconds experiment. They do clearly see waiting long time makes all the detection, discrimination of downstate or upstate getting really bad. So how to deal with this problem? I think these two groups did a lot of work to make this surface clean. So a lot of noise, not only nearby, but maybe from the electrode comes. So to suppress this one as much as possible, a lot of effort is done. But our work is, we think it's a much simpler way. So basically, instead of qubit ion, we may put other cooling ion. Then anyway, they have a Coulomb interaction. So even we turn up the light, so these two still continuously cooling down. So and then when we choose particularly for the ytterbium barium ion, because the ytterbium's cooling laser is about 800 terahertz, and the barium case is about 600 terahertz. So 200 terahertz difference makes almost no influence when we use a barium ion. When you cool down barium ion, almost no influence to the ytterbium ion. And also mass-wise pretty similar. They can cool down each other, not that bad. So this is a really simple idea. So and then when we try this one, we thought we could have easily really long coherence time, maybe days and something like that. And then we found other problem. So we eventually applied the dynamical decoupling pulse. Just let me skip this some jargons a little bit. Anyway, our clock itself was not that good enough, so we need to keep compensating about it. So anyway, we did this one. So it should be really good coherence time, but no matter what we did, we cannot go over about 600 seconds. So that this contrast slowly decay, and then about 10-minute level, all this the 1 over E decays already happens. Anyway, so this is our first steps to make about the minute levels coherence time to 10 minutes, and then still we don't know what's the problems. So in principle, it should be again the limit by the decaying of T1, then it should be million years. So we're digging out the problem. Maybe this is, although it's a 0 to 0 transition, so close to the magnetic field insensitive state, maybe magnetic field would be a problem. So we put the magnetic field shielding surrounding to our vacuum chamber. So this one indeed really helps. So we had some magnetic field sensitive qubit, the G-man qubit, coherence time increased to about 0.5 millisecond to 20 milliseconds, about 40 times coherence time is increased because we put the shielding of a magnetic field. But for the qubit, the clock qubit, nothing happens. Still, it's limited by 10 minutes. It's not helping at all. So we didn't understand. So we tried maybe when you apply the microwave, there's some leakages. So we put the everywhere switches before going to the microwave applications, and that looks like a short time level. It helps. And also we thought about maybe this ytterbium cooling laser somehow leaked. So we have the 3 stages of blocking. So EOM or AOM, and eventually we decide to mechanically block. So no light is going through the chambers. But still, that didn't help. So we really puzzled by this one. And then the conclusion is so ridiculously simple. So the conclusion was, before we use a rubidium clock to stabilize the whole microwave system, that was just a limitation. So when we change it, this one's crystal oscillator, about 1 order better this frequency stability. So we are comparing, basically when we measure the coherence time, we are comparing to the atoms superposition and then microwave oscillation. Our microwave oscillation stability was not good enough to show over 10 minutes. So when we change this one to the rubidium clock to the crystal oscillator, immediately we observe this coherence time increase almost order of magnitude. So this is horizontal axis time, and then the vertical axis is again 1 over e decay. So this dashed line is our old works about 10 minutes, and then it extended to the close to 1 orders. So the over 1 hour coherence time. So we achieved, but it's nothing really we did. All we did is just changing the rubidium clock to the crystal oscillator. Only that helped. So already now we know atoms coherence time is already very, very good. We cannot detect about it. So that was the main message of, again, even 10-hour coherence time is something like this. So then we really seriously digging out what is the technical limits to see the really millions of coherence time. So here is roughly million year. So the first step is basically the phase noise of this our microwave. So and then the second level is still a little bit of magnetic field fluctuation, and then a certain level maybe ion hopping can be a problem and so on. So we thought now we fully understand what's going on, and then just nothing much interesting things happening. But
what is ion hopping? As you use it.
Right. So the ion hopping means it's kind of related to the the sympathetic cooling. So the
fluctuations trapping potential.
No. Sometimes the ytterbium ion is left, but sometimes it changes to right. So this 2 ytterbium barium atom is sometimes exchanging, and then depending on position, magnetic field is a little bit different. So that's how atoms feels different environment, something like this. So anyway, this ion hopping, if you put in the cryostat, maybe can be gone. So anyway, we thought it's nothing more interesting. So we are done about it. But anyway, this is for us world record, and our funding agency really liked it and asked us to push it more. So if you push it and 3 times more coherence time, they will give some substantial amount of fundings they will provide. So it's really, I feel like boring problem. So all we need to do is now maybe 3 times better the crystal oscillator, and that's all we need to do. And when I visited the University of Sydney, they had the 10 times better crystal oscillator, cost about $200,000 US. but they don't sell to any other countries. So somehow they want to make some good business out of that. And anyway, I feel it's very boring. Why we want to do this one? Just very boring measurement and so on. So we're thinking about making a little bit fun about it. And then that's how we think about called the decoherence-free subspace qubit. So the main idea of this one is basically instead of one ions, two state, we are using two ion, and then the two ion, one state is down, up, the other state up, down. So we name this one is down, the other one is up. So then it's called this energy level basically is the same. So the coherence between them is really well maintained. And also this I feel like it's better than simply replacing the crystal oscillator 3 times better one. So and indeed this David Wineland group shows when they do this kind of encoding, if individual qubits coherence time decaying rapidly, but this decoherence-free subspace stay there very long time. So this is basically indicating how long you can, the amount of superposition you have. And then the Innsbruck people, Christian Roos and Hartmut, they show each one is about millisecond coherence time. But when you put in this kind of 2-qubit encoding, and then close to the several hundred milliseconds, and even over like 20 or 30 seconds they observed. So I thought this maybe a better way to do it. So indeed that's all we did. So instead of now the Kihwan qubit, we have again the same clock qubit. So our have a same clock qubit, and then if we put this kind of up down is up, down up is down, and then basically the energy level of these two essentially same. So this qubits difference, before it was 12 gigahertz, but now this is nearly 0. So the phase noise basically gone. So no matter what oscillator we use, because it's same level, we don't need to worry about the phase noise. And then the magnetic field gradient, also magnetic field noise is gone. Basically this two ion separated by about 10 micrometer. So the only little bit difference between them matters. So overall fluctuating magnetic field, we don't care. So all this phase noise and then the magnetic field fluctuation should be gone. So we expected it should be really good. And then now it's a bit almost that's basically ideas. So and then a little bit detail of how to measure this one, but let me skip this one. So Christian Roos, they developed very nice technique of correlation spectroscopy. So the overall contrast in this case reduced to the 0.5. But other than that, we do really see when we do this decoherence-free subspace coding, and then up to we measure about half an hour, we barely see this decaying of contrast. Actually, we repeated this one is 100 times. Only, I think 2 events is showing a little bit changes. So we are not sure this is really decaying or not, but anyway, that's how we observe. So if we just think about error bar, within error bar, it's not decayed. But anyway, given this situation, we do see about 10 hours of coherence times. And so that's more or less all. And then at the end, I just a little bit adding some technical details. So we want to know what's the really limiting factor in this situation. So instead of the clock qubit, we also prepare the Kihwan qubit. And then from that, we know that this 2 levels tiny bit difference is about 0.1 hertz. So the clock qubit case, Kihwan qubit is 0.1 hertz. So the clock qubit roughly 300 times smaller. So it's almost a negligible energy difference. And then by measuring this Kihwan qubit's the coherence time, roughly is about 145 seconds with this Gman qubit. So if we just infer from this number to the this clock qubit, roughly we have to multiply 300 times. So the over close to day level coherence time we should have, but our statistics showing about 10 hours. And then on top of that, some other some tricks we need to do is in our trap we want to have this kind of configuration, but still we have some ion hopping problem. So sometimes we do have this reconfiguration, and then by pushing the RF up, we can always bring back this one and so on. So some simple techniques we need. But other than that, basically here, this coherence time, we observe over 10 hours. And then again, confirming all the previous messages, our coherence time is not limited by fundamental principle, but just simply technical limitations. And then what can we do more? And so can we really use this one as a qubit and much better performance computations and so on. So when I was in Innsbruck, and this we tried to realize a gate out of this logical qubit, and somehow the performance is worse. So surely also indicating all our controllers is a limitation, not the qubit property itself. And then we may eventually this memory aspect, so that we just using basically single qubit, making a superposition and see how long it lasts. But maybe we can make eventually entangled state or more sophisticated state, see all of them can be maintained very long times or not. Or also anyway, this is really long coherence time, hour level. So eventually maybe it could be a good candidate, maybe quantum money, or I shouldn't know. I already contacted this Charles Bennett when we had a 1 hour coherence time, and now it's 10 hours. So I don't know what he would say, but and then maybe quantum metrology, something like this, we could think of. Okay, so time is still going on. Yeah. So this is all about coherence time improvement, and so the end of year is our funding agency's review. I hope they would be satisfied about it, and they said, what do you want to suggest after that? So I said, done with this. So no more, no need to further explore this one. That's what I want to say. And then in our trapped ion community, one of the problems that we are considering is how to scale up. So nowadays, our competitor, like a superconducting system or neutral atom system, shows lots of numbers of qubits. So maybe we can also think about using two-dimensional crystals of ion. So we can realize this similar to neutral atom system, scaling up the number of qubits. So let me also quickly go through this current activity and then conclude about it. So this is when we count is about 278, and then so our idea is typically in our trapped ion community we are using the linear chains of ions. So because we are using oscillating electric field, only the linear chain has no effect of oscillating electric field. So the people try to avoid other than this linear chain. But obviously, this is our 52 ions 2D crystal compared to 1D, similar number. And this one is more located, dealing with this much better. So we think scales up more easily with a larger number of qubits if we use a 2D crystal. And then the ion trap's strong point in quantum computation is all-to-all connectivity. But if it's far away, getting worse and worse. But if you we are in 2D shapes, then still this all-to-all connectivity a lot easy to maintain. And then maybe it's naturally mapping to surface code or color code, some two-dimensional code we can intuitively mapping. And then also thinking about some 2D physics or 2D material, maybe you can some connections and so on. And then this is not original idea is not from us realizing 2D crystal. So this Innsbruck groups and the NIST group or University of Sussex, they are doing a lot of sophisticated engineering of traps. They're trying to make a 2D crystal, and but there's some progresses, but still very hard. And from the UCLA, West Campbell, and Phil Rahim, Indiana University, they had a very simple idea of instead of linear chain case is a three-dimensional harmonic oscillator with squeezing one direction. If we just squeezing plane, then we could have this 2D crystal. So we are a lot inspired by this one. And then we had some traps. Basically, it's more or less the same designs of trap that Chris gave me to use. So the same designs of traps, we just make the one piece. So we made a monolithic trap. And we realized this is a really perfect choice for making 2D crystals. So here, instead of this before we had the linear chains ion like this way. So the field side is squeezing this axial direction. But here we are, instead of axial direction, we just squeezing one of radial direction. So then, we have this nice two-dimensional crystal. And then here, nice part is all this oscillating electric field is in the plane. So if we apply the laser beam perpendicular to this one, we don't need to worry too much about this oscillating moment, moving of ions for quantum operations. So this is, we think it's a good addition to the trapped ion community. But beginning of traps has a really bad performance and so on. So for the past years, we need to improve surface roughness of our trap. So you see some wiggling part of our original trap is made of alumina and then cut by lasers. And then also on top of that, we put the gold coating. And then in order to connection, we do the laser cutting and so on. So that fill out some of gold. And so in trapped ion system, whatever dielectric exposed is really bad. So that all bad things happen. And then we basically the same as Novot Link's trap. So instead of alumina, we use glass fused silica. And then basically it's a 3D printing method. We don't need to worry about correctness of dimension by just this laser provide about the micrometer precisions. With that, we made much better traps. So in the beginning, this kind of development, in the beginning, barely we made about 40 ions in our system. Now we just one day we tested how many ions we can load and so on. But at least 500 ions we can load. And last week there was some Chris Monroe's 60-year birthday party organized by Novot. I saw the 6,000 of ions also there. Anyway, the people are really doing well. So we should keep moving on. But anyway, this ions scaling up system, this is could be seems one of the ways. And then we also improved the one of the trapped ions technical problem is called heating rate. You already see some heating problem, and then this new traps also much better performing. So we think it's somehow good to go and so on. And then anyway, in the beginning with very bad traps, I did a quantum simulation. I learned the quantum simulation from the Chris Monroe. So we extend just a 2D crystal instead of a 1D. We just made a 2-dimensional crystal, and then everything anti-ferro interaction. In the 1D case, there's no frustration. As you see, down, up, everything just different pair. So all they are happy about. But once we made a 2D, so this one tried to be down, but this one tried to be up, down, up, and so on. So middle one is a bit frustrated. So every pair cannot be happy about it. So that's why it's in the end, ground state wise, middle guy is up, down, down, up, all configuration is in superposition. So this is one of the signatures of frustration. And our 2D crystal indeed showing when you had this 7 ion, some situation, indeed this kind of 4 different state is emerged. So we know this is really working. And also we have a not fully universal programmable controller, but some controller made, then the stripes types of ground state appear, or the left and right types of ground state appear, something like this. So we feel it's kind of working, and then we reported about it. But nowadays, other the groups made a much nicer works and so on. But when we did this one, we barely made about 10-ish ions experiment. And with a better controller, better traps, now we are thinking about doing some kind of entanglement in our trap. So it's called spin squeezing. So the basic idea of spin squeezing is all the spins, basically, they are forming some entanglement in Bloch sphere. So because of uncertainty, they have this kind of shapes. But some way, if we add some kind of this kind of spin-spin interaction, it's squeezed like this. And the 2-dimensional system is working really well. This group shows. And then the 1D chain, in general, it shouldn't work. But some theory people, smart theory people developed, instead of this Ising interaction, if we change it to this XY interaction, hopping interaction, somehow you can make also nice spin squeezings. And then, we think about this one and showing our system's capability of entanglement is a good chance. So that's how we jump in called 1x twist to 2x twist spin squeezing. So here, I'm sorry that I'm skipping many things and so on, but anyway, people did twist is 1 axis, something like this. And ideally, if we have a 2 axis twist, so not only one spin interaction, if we have the other one, you have a more perfect squeezing you can make, a more perfect entanglement you can make. And then now recently the Junjian's groups with the polar molecule and James Thomson group, atoms in the cavity, they did something similar about it, but they didn't see this spin squeezing with this 2-axis twist case. And then our case, our interaction is very simple. So when you do the quantum simulation one, similarly this way, we can have a more or less this interaction by just changing the laser beam in different way. We can have this minus sign. So this 2x twist is really simple to realize. So indeed, we do see the 1x twist or 2x twist really happening, similar to previous other guys. And then these two gentlemen indeed shows about the spin squeezing about minus 4 dB level, similar to previous groups. So we are also pretty happy about it. And then in this 2D crystal case, for now, we did the first quantum simulation with the frustrations, and then we showed this trap indeed can show some entanglement in system, and hopefully with much larger one, we can extend to the many other physics we can explore with this system. And then we're also thinking about some not only quantum simulation, but maybe universal quantum computation. So this is our ions, maybe some geometry, and inspired by neutral atoms. So we're adding whatever individual beams, and then we can do some on and off controls about it. So this is some movie of laser beam, not the ions. So the laser beam, we could have some on and off individual controls. With that, with also some simplified some schemes, we may able to scale up this hundreds or more trapped ion quantum computation can be realized. So that's I'm quickly go through this one, and then finally so thanks for your attentions. And
Thank you. Questions?
So, I mean, I know the reason for linear change is to avoid micromotion, so I don't quite understand why micromotion isn't bothering the crystals.
thank you for your perfect question. So yes. So only this linear line, there's no micromotion. Whatever outside, you should have a micromotion, right? And then but in this kind of traps, so all the micromotions in this plane. So
it's in the plane perpendicular to the crystal? It's in the
yeah,
plane with the crystal.
in the plane of crystal. In the plane of crystal. So let me have a example of this one. So we do see that 2D trap in the side view. So the middle, we have some RF electrode. Outside is DC, is making sense. Then in the middle, all the electric field oscillation is in this plane. So that all ions movement going up and down in here. So if you apply the laser beam perpendicular to this plane, and this ion will not see any frequency changes because of Doppler shift. And then we do see here we can really resolve all the motional mode, all the coherent evolution can be realized by simply putting the laser is perpendicular to the micromotion. If laser has a little bit angle, and then all ruined, we cannot see anything. Thank you.
Have you looked at the coherence times in your system if you have a larger system like the 2D crystal that you showed, and you showed 10 hours with, I guess, a pair of ions? How do these results sort of change when you go to larger systems?
That's also a very good question. So we believe every qubit is identical. So the ion is here or here, whatever. The coherence time shouldn't be different. So each ion, single ion, more or less about our levels of coherence time we can have. So when you have many ions, in principle, you should have such things. But really like this, maybe not, because one of the problem is when you have a multiple ion, I a little bit cheating about it. So it's not always there. We need something to maintain. A single ion is always there, but a multiple ion, at a certain point, some chance to escape. This one maybe hours, sometimes 10 minutes, sometimes maybe very long time. So maintaining this one is one of the challenges. But in general, in principle, no matter where you are, the coherence time shouldn't be much different.
Yeah, I have a very naive question. How many qubits at most do you think can fit in a single 2D trap. And do you think in the future people need to go to a more modular design?
Right, yeah, that's a really, I don't know, it's kind of our secret project, but should I say? That's really, really good question. So sorry, not this one. So right now, the entrapment ion community, the modular design with ion shuttling. So once you succeed ion shuttling, you can put whatever number of electrode, you can go further and further. And how about these 2D crystals? Although we do see, I do see about extending horizontally a lot, like 6,000 atoms be there. Can we have some kind of modular design out of that? I mean, that's a really good question. We believe we have some answers. So what we are, should I say about it or not? Can we?
We're all friends here.
Okay, yeah. So I don't know if it will work or not, but what we are considering is we have this is one crystal like this. We may have another crystal, and we have another crystal, something like that. And then maybe this one is a little bit of connecting. So then, whatever here, we are not sure we can push 100 or 200 or 500, but then we may have another one. So that inside it should be all to all. But in between, we have some amount of connections, then it can be modular and so on. That's roughly we are thinking about, but it's a really ideal level. We never seriously yet digging out how much you can do and so on. But that's rough idea. It's a really good, it's not a naive question. It's a really important question, you can say, yeah.
All right, I don't see any other question. Let's thank Kihwan again.